All right, well, you may be wondering at this point, why are we inserting a lecture on heaps right into our discussion on graphs? Well, it turns out that the last graph algorithm we discussed, which was Dijkstra's, can be greatly improved by using a heap. So let me remind you what Dijkstra's does. At each iteration, we continually look for the value that minimizes Dijkstra's greedy criterion. That sounds an awful lot like what a heap is good for, continually getting a minimum value. So if we have this running time as it is before, we computed that the total running time was big O of n times m, because we were sort of blindly looking for the minimum path in each iteration of these inner two loops here. In fact, we looked for the minimum, and then we just threw out all the information that we had from the previous iteration, and we, in the next iteration, look for the minimum again, even though we've only added sort of a minor amount of information. We've only added one vertex and all the edges associated with that vertex. So let's look at a way to improve the performance of Dijkstra's. And for this first one, I'm just going to show you a very practical algorithm for computing Dijkstra's, and then later on in the next set of lecture slides, we'll look at sort of the state-of-the-art method, which uses something more complex than just a heap, something called a Fibonacci heap. So what we're going to do today is look at an algorithm for solving Dijkstra's algorithm in big O of m log n instead of big O of m times n. And later on, we'll look at this more state-of-the-art technique, which is even better. All right, so here's our code for Dijkstra's. And this is not going to be pseudocode. This is actually going to be Python code. And again, this is big O of m log n, which isn't optimal, but this algorithm turns out to work very well in practice. And it turns out to be very sort of easy to implement, which is why we're starting with this version and not the Fibonacci heap version. So I'll just grab out the length of the adjacency list, which gives me n, and we'll set the path links to all vertices as infinity to start with. And then we'll say the predecessor of each vertex is none to start with. So here we're not just going to compute the optimal path links, we're going to compute the paths themselves. And for that, we need to say, well, how did I get to a given vertex? If I came to that vertex from the start vertex, then that's done. And I'll show you how we can use this list of predecessors to compute the paths to every other vertex from the start vertex. Okay, well, we have path links, they're all set to infinity. We need to initialize the path link to the start vertex to 0 and the predecessor of the start vertex to none. And then the rest of this is fairly similar to what we had before. We have our set of found vertices, and now we're going to create a min vertex heap. So this is our heap, and we're going to store in it the vertex to which we want to travel, or to which we know a computed path, a computed shortest path so far, and then the key values themselves. So the values that are going to dictate how elements get stored in the heap is going to be the length of that path. So this is a vertex. You could think of this as sort of the payload or data. And this is the key value used in the heap. So all the way back to a picture I showed at the very beginning of this set of lecture slides. Our data is the vertex we want to go to, and the key value is the shortest path to that vertex. So if you were curious at the time why I was using that as an example, that's because we're coming back to it here. So that's what's in the heap. So to start with, we have the start vertex, and it has a key value of 0. So we just have this single value in the heap. And then while we haven't found every vertex, we're going to pop off that minimum vertex, add it to the set of found vertices, and now we're going to loop over everything that vertex to which that vertex is connected. We're going to compute path links to all of those vertices, and if it's less than the path link that we've seen so far, that's good. So we will set the path link to it. Remember, they all start at infinite. We'll set the path length equal to it, and we'll set the predecessor. So we came from this vertex, and we're going to this vertex. So v from and v2. And then we push it onto the heap. And then at the very end, we can just return the path links and then return the paths themselves, which is stored in this predecessor's set. All right, well, that's a little opaque. So let's look through an example And really all this code up here is just setup code for creating the heap, creating the path links, creating the predecessors, and initializing them correctly. So all of the code I'm going to show on the next slide is really just this loop, the while loop where we're actually doing the work. So let me start by just doing this initialization. Let's say we have this graph. We can pick any vertex we want to as the start vertex. And actually the way I've created this graph, sort of any of them can be the start vertex. So let me just pick one at random. And just for fun and because I can't help myself, I wrote a little bit of Python here that I'm just in a Python REPL. And I've got my vertices A through F. I imported the random choice function and I'll run it. All right, so our start vertex is going to be the vertex B. All right, so B is our start vertex, which means it's already in the heap with a path length of 0, and it's already in the found set. I'll just denote that as checking B off. And what we do is we pop B from the heap. So popped it from the heap, and now we loop over all of the edges connected to B. So V from is B, this first iteration. We compute the path links as, okay, well, what's the path link to that vertex? So let me denote the path links in blue here. And you know the path link to B is 0. And we should also say their predecessor. So the predecessor of B is none. Okay, well, we'll compute, and everything else is set at infinity. So maybe I should mark everything else as having path links of infinity. And their predecessors all get initialized to none, but we'll change those as we go. All right, so the path length of each vertex connected to B, so that would be C and E. Let's go to C first. We're going to compute it as 0 plus the weight going between those two. We'll compute that as 2, which means infinity becomes 2, because 2 is less than infinity. And we're going to set the predecessor equal to B. So its predecessor is B. Then we push that vertex onto the heap. So the heap now looks like this. We have a vertex with a path length of 2, and the vertex is C. That's on the heap. Now we do the same thing for the next vertex to which the vertex B is connected, which is E. So we will erase that its path length is infinity and mark it as 2, so those are both 2. And its predecessor is B. And we push it onto the heap. So we always put it at the last slot in the heap, so it's going to go here, and it's the vertex E. We are not violating the heap property with those two vertices. They can be greater than or equal to the parent vertex, or the parent node in the heap. Okay, now in the next iteration of the while loop, we pop off the heap min, which happens to have a from length of 2 and a vertex from of C. So we add C to the found set, which means we now know the shortest path to get from B to C is a path length of 2. There's no shorter way to do that, and we'll prove that in just a few slides. Now we look at all the connections, outgoing connections for vertex C. So C has a connection going from C to D, which has a path length of 2 plus 8, which is 10. So we'll mark out the infinity and we'll put 10. And we'll put the predecessor as C. We may later on find a shorter way to get to D, but that's what we have so far. Oh, I need to update our heap as well. After I extracted that node, this 2 came up to the top. We had to bubble up the 2, which, not much bubbling up since they were the only vertices in the heap. So at the top of the heap now we have a 2, E, and we've just added a vertex D with a value of 10. That does not violate the heap property, so we're done with that iteration. Well, we still have, no, we don't have any of our outgoing vertices from, outgoing edges from vertex C. So we're actually done with that iteration too, which means I can erase that 2 in the C. Okay, so in the next iteration, again, we pop the min value from the heap, which again is a 2 for the V from length, and it's a E for the vertex. So now we look at all outgoing edges from the vertex E. Oh, and we've got to check off that we now know the shortest path to that vertex. So I'll put that in there. Okay, so it has 2 outgoing edges. So in this current iteration, we're going to add F. Maybe I should do these alphabetically. So we'll do D first. So we're going to go to D, and that's going to shorten up the total path length from 10 to 7 plus 2, which is 9. And it's going to change the predecessor from C to E. And now we're going to add that node to the heap. And we always add it at the end. Oh, but before I do that, I should actually change our heap. So we pop them in, and then we have to move this value up. So at the root of the heap now we have 10 with a value of D, or data of D. And that's important because now we're going to have to insert a new node that is 9, a key with 9, but also with a value of D. So there were 2 different ways to get to D. We could go through C, or we could go through E. And it turns out this second path through is actually cheaper. So we inserted this, but that's a heap violation, so we have to bubble it up, which basically just means swap these 2 nodes. So the easiest way to do that, since they're both D, is just for me to put the 9 here and the 10 here. All right, so that's the current heap. But we also now need to update F. So we'll scratch out this infinity, and now the total path length to go from the start vertex to F is 2 plus 3, which is 5. And the predecessor vertex for F is going to be E. Now we have to add that to the heap. So we always add it at the final spot in the heap, which means I'll put a key value of 5 here. That's the path length. And the vertex itself is F. But that's a heap violation, so I'll need to swap those 2 nodes, which means my resulting heap, I'll just draw this down below so I don't get confused, is now this. So that's our new heap, and we can trash the one above. And now you might be wondering, is it okay to have 2 vertices, or basically two paths to the same vertex in a heap? And yes, it's okay, because we update the predecessor only if we find a path length that's smaller. So that's right here. Only if we find a path length that's smaller. So the value of if we have multiple copies of that vertex in the heap, the one that we should pop first will always be at the top of the heap. The one where that actually corresponds to the current predecessor as marked here. Now, I could continue going through this example, but I think what I'll do instead is I'll stop this example here. And if you have any questions, please feel free to come to office hours. If you want to continue going through iterations and you want me to check it off, feel free to come to office hours. But now I want to show you how we can use these predecessors to compute the total paths. So let me take one of these for example. So if we have the vertex D, its predecessor is going to be E, and its predecessor, the predecessor of E, is going to be B. So if we want to find the path length, all we have to do, oh, and sorry, the predecessor of B is none. All we have to do is go to the vertex to which we want the path, and go to its predecessor, go to its predecessor's predecessor, and keep doing that until we get to none, and that means that this is our start vertex. So what does that look like in code? Here's code for it. We can say, okay, here's our end vertex. Here's our set of predecessors. The path starts with the end vertex. So we initialize it that way. And then we say, okay, what's the predecessor of that end vertex? And we just keep looping until the predecessor is none. That's going to indicate that we've hit the start vertex. And all we do at that point is just keep appending things to the path. And then at the very end, we just have to reverse the path to make sure it's in the correct order, going from the start vertex to the end vertex instead of from the end vertex to the start vertex.